Hey y'all, we're going to do that practice worksheet on molecular shapes and electron geometry. There is a big difference between the two, although they're related, and I think it might help to kind of go through and understand the difference between those two things. So first let's talk about an electron group. Oh, let me go ahead and change pens here, sorry. Electron group can be a single bond, a double bond, a triple bond, or a non-bonding lone pair. So anytime you have two dots, it's called a lone pair. I'm going to write that because that will likely show up on an exam and you need to know the definition of that. Okay, so any electron group would be a single, double, triple, or a lone pair. Let me give you an example. So if we have like carbon dioxide, with carbon dioxide, I have a double bond here and a double bond here. I would say that carbon has two electron groups on it. Okay, let's see something else like NH3. NH3 would be N like this. NH3 has 1, 2, 3, 4 electron groups too. So it says 4 electron groups. One happens to be non-bonding, happens to be a lone pair, and that's going to be pretty important here in the future. All right, so now that I think we have an understanding of what an electron group is, let's go ahead and make a table that's going to help us figure out the difference between electron geometry and molecular shape. All right, so I like to remember it like this. It usually starts with 1, 2, 2, 3s, 3, 4s, let's see, 4, 5s, and then to make sure the pattern gets thrown off, we're going to only put 3 6s. Okay, so we got 1, 2, 2 3s, 3 4s, 4 5s, and 3 6s because we like to mess with you. Okay, this is actually going to be electron groups. So when you draw a Lewis structure, if it has a certain number of electron groups, you're going to go to that particular row. Then we're going to have, of those electron groups, how many are going to be lone pairs? So the order is going to go like this: 0, 0, 1, 0, 1, 2. And then for the 5s, 0, 1, 2, 3. Oh, I think I put 5 5s, huh? My bad. And then for the 6s, 0, 1, and 2 is the max you can have for the 6s. Okay, so let me go over that pattern again. We went 0, and then every time we started a new number, it went up by 1. So 0, 1, and then we started the 4, 0, 1, 2, and then the 5, 0, 1, 2, 3, and then the 6s, 0, 1, 2, because they're messed up. All right, so that's going to be for the number of lone pairs a particular thing has. Its electron geometry will be as follows. So anytime you got 2 electron groups, it's going to be linear. Anytime you have 3 electron groups, it's going to be trigonal planar. And you should have already studied this enough that you know what I'm talking about when I'm doing abbreviations. For the 4s, they're always going to be tetrahedral. So anytime something has 4 electron groups, it's going to be tetrahedral. Think of it like Tetris. There's 4 shapes in Tetris. All right, for 5 things, it's always going to be trigonal bipyramidal. And then for the 6 shapes, it's always going to be octahedral. Okay, so the electron geometry, in case you can't see, depends on the number of electron groups. But when you change the number of lone pairs something has, generally that shifts the shape, and if you watch the video that I suggested, you're going to already have a good idea of why that is. I unfortunately don't have my model kit, and so it's killing me not to be able to do a better lecture on this. So make sure you watch that and get a really good idea of how bond angles change. Okay, next we're going to look at molecular shape. So molecular shape for a linear thing is going to be linear because there are not going to be any lone pairs. Then for when we have 3 electron groups, if you have 0 lone pairs, anytime you have 0 lone pairs, the molecular shape is going to be the same as the electron group. So this is going to be trigonal planar. But if you have 1 electron group, this will actually become what we call bent. For tetrahedral, again, if you have 0 lone pairs, the molecular shape and electron geometry are the same, so this would be tetrahedral. If you have 1 lone pair, it becomes trigonal, pyramidal. And if you have 2 lone pairs, it becomes oddly bent. Again, this bond angle is actually about a little less than 120. This bond angle is actually quite a bit less than 120. So these are 2 different bents. One has an electron geometry of trigonal planar, and one has electron geometry of tetrahedral. Then we move on to the 5s. If we have none, again, this is going to be trigonal bipyramidal. If you have 1, we're going to call it seesaw. If you were to actually make the shape, you can see that it actually goes back and forth, kind of like a seesaw. It's pretty cool. If you have 2 lone pairs, it's called T-shaped. That's because it actually looks like a T. And if you have 3 lone pairs, it actually goes back to being linear, and it's going to be 180 degrees. And this is one that people love to throw on exams. They love to test you and throw 5 electron groups on there, 3 of them are lone pair, and see if it's linear, because it's kind of counterintuitive. 0 lone pairs, octahedral, will be octahedral. If you have 1 lone pair, it's called square pyramidal. Square has an E on it. And if you have 2 lone pairs, it's square planar because it looks like a square in a plane. Okay, so once you've gotten this entire thing, and I'll zoom out in case you want to like randomly screenshot it, then you're set to really understand shapes. Let's go ahead and do our worksheet, but I'm going to add one more thing here. I'm going to add hybridization. If you watched my hybridizations shortcut, you already have an idea for how it works. So I expect you to know that before we go through this. I won't give a lecture on that right now. Okay, without further ado, let's go ahead and begin. We got a chlorite ion that is ClO3 negative. We discussed in making Lewis structures quickly that if it's got a negative sign, the negative has to go on the most electronegative thing. In this case, that would be oxygen. We know that chlorine's going in the center. And so in order for oxygen to have a negative formal charge, it has to be single bound. So we're going to have one single bound chlorine, or chlorine to oxygen, and the other ones are going to be double bound. Now, if we go through and look here at chlorine, it has 7 valence electrons. So right now the formal charges here for oxygen are 0. Remember, valence minus sticks minus dots. this one's 0, and this one's -1, but chlorine isn't. So we can't forget our original steps in calculating the number of valence electrons each of these has. So here we've got 6 plus 6 plus 6 plus 7 plus the 1. From here gives me a total of 26 valence electrons. So let's go ahead and count. We got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Wait a second, I'm missing 2. What a convenience. If I put them on there, now my formal charge of chlorine, remember formal charge is valence, so it would be 7, minus the number of 6, 1, 2, 3, 4, 5, minus the number of dots, which would be 2. So now that has a formal charge of 0. So the only formal charge we have is -1, and it's on an oxygen, so we are good. All right, the next question is the electron geometry or hybridization. We know that this has 1, 2, 3, 4 electron groups. Anything with 4 electron groups is going to have an electron geometry. Oh, I just realized I put hybridization there. Yay! Anything with 4 electron groups is going to have an electron geometry of tetrahedral. You can prove it to yourself by going back to this thing, anything with 4. The hybridization is actually based on this electron geometry. So hybridization, if you remember from the shortcut video, we go S, then there's 3 P's, and then there's 5 D's. And you just count the electron groups. So there are 4, 1, 2, 3, 4. So we just go S, P, P, P. So its hybridization would be SP3. The hybridization of the chlorine would be SP3, again, because there's an S and 3 P's. The molecular shape, however, is based on the number of lone pairs. So we know that the electron geometry was tetrahedral. The molecular shape is going to be 4 with 1 lone pair, which is going to be trigonal pyramidal. Trigonal pyramidal. The next question I ask you is whether or not it is polar. Well, a trigonal pyramidal is shaped like a triangle. Again, I wish I had my molecule kit. So it's going to be like this. So if it's going to be polar, that means there's going to be an unequal sharing of electrons. So your question is there an unequal sharing of electrons here? Well, absolutely, because there's going to be a pull down here, and a pull down here. It's going to be unequal, and this is going to be polar. The only case you would not have a polar thing is if they were all pulling exactly the same apart from each other in a different direction. Another thing to think about with this particular thing is that it's resonating. So I could even ask you the bond order of this. How did I know it's resonating? Because there's 3 things and one of them is being treated unequally. So what if I asked you the bond order? Well, the bond order would be 1, 2, 3, 4, 5 bonds shared between 1, 2, 3 oxygens. So 5/3 or 1 2/3. All right, moving on to this next thing, sulfur trioxide. Sulfur trioxide, I got an S and 3 oxygens. That'd be a total of 4 times 6 or 24 valence electrons. As I go through, I look at the oxygen and I see, hey, look, it looks like oxygen's all going to be neutral. This whole thing is neutral. So chances are those oxygens are going to be double bound. So I go ahead and double bind them and we'll see what happens. We know that oxygen, when it's double bound, has a formal charge of 0, and that's what we ultimately want to get. And sulfur also would have a formal charge of 0 because it's got 6 valence electrons, minus 1, 2, 3, 4, 5, 6 sticks, minus 0 dots for a formal charge of 0. So each of these has 0, and the sulfur also has a 0. Keep in mind, sulfur is anything in the 3rd row or below, same kind of thing with chlorine. Anything in the 3rd row or below can break the octet rule. All right, now we get to its electron geometry. Its electron geometry has to be trigonal planar. There's 1, 2, 3 electron groups. There are no lone pairs on this thing, so its molecular shape will also be trigonal planar. I'm sorry, I forgot to do the hybridization, so let's go ahead and do this. Hybridization is based again on the number of electron groups. We have 1, 2, 3. So I go SPP. In other words, it's SP2 hybridized. That sulfur would be SP2 hybridized. Now we get to the sulfate. Sulphate would have a total, same as its SO3, or excuse me, this is sulphite, I just saw that. Sulphite would have the same number of electrons as this SO3, but plus 2 more here. So 2 plus 24 gives me 26 total valence electrons. Now I notice that it's got an overall charge of -2, telling me that 2 of those oxygens will likely be singly bound. Let's go ahead and see if we make it work. All right, and if we went to count the electrons right now, we'd get 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, missing 24. But if you calculate the formal charge of the sulfur, you'll actually find that it's +2. Because valence is 6, minus 4 sticks, minus 0 dots gives me a +2. So this oxygen here has a -1 formal charge, this oxygen here has a -1 formal charge, but this sulfur has a +2, and I can put 2 electrons there because I was missing 2. Now I have 26 electrons accounted for, and everything looks pretty happy to me. Would this resonate? Absolutely. And oftentimes you'll be asked about the bond order when things are resonating. So let's go over here and just do it for fun. The bond order would be, you are sharing 1, 2, 3, 4 bonds across 1, 2, 3 atoms. So bond order is 1 and 1/3. All right, so now we can move on to the electron geometry and hybridization. The electron geometry of this, we have 1, 2, 3, 4 electron groups on the sulfur, so it's going to be tetrahedral. The hybridization is based off of that, so going through the 4 things, we've got SPPP, so it's going to be SP3, hybridized. Now the molecular shape is going to be a little bit different because we have 1 lone pair. So in this case, we want to either hopefully have this memorized and have an understanding of why we get what we get. But I know that this is a little bit rough. So we've got 4 electron groups. 1 of them is a lone pair, and that's going to be trigonal pyramidal. Trigonal pyramidal. A trigonal pyramidal kind of sits like a pyramid. This. So I've got an oxygen pulling this way, an oxygen pulling this way, an oxygen pulling this way. And overall, if it's a game of tug of war, which is kind of like how I think about polarity, somebody pulling here, here, and here, the overall sulfur is going this direction. So the sulfur is going down, and this would be polar. I forgot to do that up here. This would not be polar. Everything is perfectly in a plane. All right, now we get to an interesting one that I could see showing up on an exam and really throwing you off. N2O, and you're told that N is the central atom. So if you calculate the total number of electrons here, we have 2 times 5 plus 6, which is 16. And you might go into this drawing, let's say, and I hate to do this, but I want to make a mistake. Let's say you go into this and you're drawing it and you're like, okay, well, the overall charge is neutral, so I'm going to go ahead and say oxygen is double bound. And then you think, okay, well, nitrogen is not in period 3 or below, so you can't break the octet rule. So let's give it an octet. And again, nitrogen over here would have to have an octet. And that looks great. And if you count all the electrons, we've got 2, 4, 6, 8, 10, 12, 14, 16. And everything looks pretty. Everything's got an octet. But don't forget to look at formal charges. If we go and look at formal charge of this oxygen, it would be 0. Of this nitrogen right here, 5 minus 4 would be +1. And this nitrogen over here, 5 minus 2 minus 4 would be -1. Okay, so we've got a 0, +1, and -1. If you remember your formal charge rules, where do the negatives have to go? The negative formal charge has to go on the most electronegative atom, which would be oxygen over here. We have to have a negative on this oxygen. We cannot have it on here to have the most stable structure. Although this is a resonance structure of N2O, it is not the most stable. So let's go ahead and draw the most stable. Let's put the -1 formal charge on oxygen, which we know would be a single bound one. And then do the only thing we can do, give each other nitrogen an octet. Now, if you go through and calculate, let's count valence electrons to make sure. We got 2, 4, 6, 8, 10, 12, 14, 16. So we got 16 valence electrons. This nitrogen, anytime nitrogen is triply bound, it's got a 0 formal charge. But this one would be 5 minus 4 sticks minus 0 dots would be positive 1. There's no way around this. Usually when you have a negative one and a positive one, you want to draw a line between them, but then we would break the octet rule with nitrogen, and we can't do that. All right, so this is the most stable structure. And now let's move on to the next part of the question, which talks about the electron geometry. It has 1, 2 electron groups around it, so it's linear. Its hybridization, therefore, would be 1, 2, would be sp. Its molecular shape, none of those are lone pairs, so its molecular shape is also linear. And is it polar? Yes, it's absolutely polar. Oxygen's more electronegative. It's pulling those electrons away, leaving a positive charge over here. So oxygen over here is getting all the electrons, leaving a general positive charge over here. So polar, yes it is. All right, moving on to the next one, SeOF2, selenium, oxygen, oxygen, and fluorine. I look at this and I think, okay, it's neutral. Oh, excuse me, it's SeOF2. So I look at this and see it's neutral, so I automatically think, okay, fluorine's gonna be single bound, oxygen's gonna be double bound. That's the most likely scenario. Then we go ahead and fill these in. Because if fluorine's single bound, it's gonna have a formal charge of 0, oxygen as well. Let's count electrons. Looks to me like we got 6 from the selenium plus 14 from each fluorine plus another 6 from the oxygen. What's that, 26? Let's go ahead and count. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. We only have 24, but that's good because if we looked at the formal charge of selenium, it's positive 2 right now. So it needs 2 more. Now, the formal charge of this is 0, 0, 0, 0, and a neutral atom, that's like the best case scenario. This one above is one of the rare cases where you won't be able to get everything to be 0 in a neutral atom. All right, now we can look at the electron geometry of it. We have 4 things around it. Looks to me to be tetrahedral. And one of those things is a lone pair, this trigonal pyramidal. If we look at the hybridization, again, that's based on just the number of electrons. We have 1, 2, 3, 4 different electron groups. And so we go 1, 2, 3, 4, that would be sp3, hybridized. Is it polar? Absolutely. Fluorine is the most polar thing, most electronegative thing, so it's pulling electrons that way. This one's pulling electrons that way. Again, this is like a pyramid, so one's pulling this way, one's pulling this way, and oxygen's not pulling as hard. So essentially, your question is the selenium here going to move in this situation? All right, I know this is kind of weird, but I really, really want to demonstrate this for you. So in case you're not getting this part, let's pretend that this part of my hand is selenium. Here I got a fluorine, here I got a fluorine, and here I got an oxygen, okay? So fluorines and oxygen and selenium. And this is what it looks like, kind of like a pyramid, okay? So you can put your, yeah, like that. All right, cool. So the fluorines are the most electronegative, meaning they love electrons. So these guys are pulling all the electrons. Imagine almost even like, yeah, no, just, they're pulling like a game of tug of war, all the electrons, and oxygen's not pulling as hard. So if these two are pulling and going this way, then selenium's moving. And the question is always going to be, is the atom that you're looking at actually moving? And yes, it would be, and that's why this is polar. I shouldn't have done that with permanent. But you know, my kids do it all the time. And we can just join them. All right. Let me go ahead and make sure I keep the same headings here. Ooh, this looks like fun. Tellurium. So this in the center, and we got 5. Fluorines around it. If I calculate the total number of valence electrons, don't forget that it's -1 charge. So I got 1 plus 6 from the tellurium plus 7 times 5 is 35. So what is that? 7 plus that is 42. Total electrons that we want to have. Now, it has an overall negative charge. So let's go ahead and see what we can do. Let's give everything an octet. But that negative charge tells us that the formal charges must add up to be -1. And right now, if I go through and calculate the number of electrons I've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40. Ooh, I only got 40, but I need 42. Where am I going to put those 2 extra electrons? You cannot break the octet of fluorine because it's not in the third row or below. There's nothing you can do with the fluorines. They have to remain this way, again, because they're not in the third row or below. They have to obey the octet rule. If you, for example, made a double bond to fluorine, its formal charge would then be 7 minus 2 minus 4, which would be +1. Fluorine's never going to be positive because it's the most electronegative thing. It's always going to be 0, just straight up always going to be 0. So the only place that we can put those 2 electrons is there. Now tellurium has 6 valence electrons minus 5 sticks minus 2 dots, or -1 formal charge. Now we have 42 electrons, and this is the shape that makes the most sense. In fact, it's the only thing that you can do to account for all your electrons and make sure all your formal charges add up correctly. Now we look at the electron geometry. It's got 6 things around it. 6 things around it is octahedral. Now we're talking. If I look at its hybridization, it's got 6 things around it. So we go up to this. We got 1, 2, 3, 4, 5, 6. We're going up to D. So it's S, P3, D2. And that would be the hybridization here. And its molecular shape, well, you have 5 things. Let's pull it up. Or excuse me, 6 things. And one of them is a lone pair. That's square pyramidal. Is it polar? So square pyramidal. I don't think I can do it with my fingers. Square pyramidal is like this, where you'd have 1 fluorine there, 1 fluorine there, 1 fluorine there, 1 fluorine there, and 1 fluorine at the top. Beautiful, right? And so these all cancel each other out, but this one right here will be pulling the tellurium up. And so is it polar? It absolutely is polar. It is uneven. Okay, now let's look at the next one. Cis and trans, we discussed in the last lecture. Cis means the same. Trans means opposite or opposing. And so I've got 2 carbons. That's telling me I've got 2 central atoms. We've got a hydrogen, and fluorine. Because we have 2 fluorines, I know that when it says same, we're going to put those fluorines on the same side. Anytime it says cis, I know we're not talking about a single bond, because there is no cis single bond things. It's a double or a triple. We put a hydrogen here and a hydrogen here, and we know that carbon only likes to have 4 bonds. It's already got 2 there, meaning this is something with a double bond. Then go through and draw the dots on the fluorine. And we could calculate for the number of valence electrons. But this one should be relatively straightforward, just because the cis gives a lot of stuff away. All right, so I didn't specify which carbon we're talking about, but oftentimes in an exam, you have a star on one of the carbons, and it will say, hey, what's the electron geometry of this carbon? Well, this particular carbon has 1, 2, 3 electron groups on it. So we're talking about trigonal planar. Its molecular shape, There are no lone pairs, so its molecular shape also has to be trigonal planar. The next question is it polar? I want you to think about it. We've got somebody pulling tug of war up here, somebody pulling tug of war up here. You have each of these fluorines pulling. Do the carbons move? They totally do. Even though the left and right might cancel each other out, overall the direction of this carbon-carbon bond, if you're pulling this way, would be up. If you don't believe me, then grab a pen and pull like this. Apart from pull one this way and one this way, and you'll pull the pen up. All right, so that is absolutely polar. Now let's move in to the next one. It's trans. Same thing, except for the fact that it's trans. So let's go ahead and do this. We'll put one of the fluorines up and one of the fluorines on the opposite side of that double bond. Go ahead and fill in the lone pairs. Again, it's trigonal planar. I forgot to do it on this one, but the hybridization would be 1, 2, 3, so it would be spp, sp2. Same with this one, sp2, if I start the same carbon. The molecular shape is also trigonal planar on that particular carbon. And the question is it polar? Well, now, grab your pen, pull one this way and pull one this way equally, and see if the carbon moves. It doesn't. I'm pulling one this way and one this way. And that thing's not budging at all. In fact, these are opposing equal and opposite forces, opposing each other, and therefore it is not polar and not unequal pull at all. All right, so a couple little things that I'd like to go through before we end this. Actually, really one little thing I'd like to go through. I can see questions very similar to what we covered being asked. I also see something like this. For example, if I starred this fluorine and asked you for the hybridization of that, just make sure you're looking at lone pairs as single electron groups. So I'd say that's 1, 2, 3, 4 electron groups. That'd be sp3 hybridized. Other ways questions could be asked like this. Which does carbon typically have? And you might have something that's like sp, sp2, sp3, sp3d. Well, an example of a carbon that's sp would be some kind of linear carbon. sp2 would be like a carbon with bonds like that. sp3 would be a carbon with that. sp3d would be a carbon with 5 different electron groups. How many bonds can carbon make? Only 4, and therefore this can't work. So that's another way that I could see a question being asked. So just keep in mind that hybridization can be asked more than just what's the hybridization. You actually have to understand how to apply it. So I hope that helps, and hope you guys rock this exam. If you have any questions, post them on the discussion board, and I will be sure to answer them. All right, y'all have a great one. Bye.